So welcome, this is Math 331, lecture 11-ish, 10-ish? I think 11-ish. I think it's 11 today. And so what we're doing today is we're doing geometry proofs and we're doing the pigeonhole principle. So we had started doing some geometry before where we were looking at points on a sphere, and we actually proved a theorem, and then the question is, how far can we push this? Can we do this on not just the circle, but can we do it on the sphere? Can we do it on the n-dimensional sphere? What kind of result can we get there? And I think that there's a really nice result that I think we can get as a class, and I think it would be a nice way to end that unit. Now, if you are a math major, you are expected to do certain things. Right? One of them is you need to be able to prove the square root of 2 is irrational. Okay, so it's worth talking a little bit about this. Square root of 2 is irrational. I think the most common proof people know is assume not. So the square root of 2 is a over b. A over b are positive integers. And what else do you want to say about a and b? You want to go down that route. Okay. So there's two possibilities. One is to say a and b are relatively prime. What's the other possibility? So method 1, a and b are relatively prime. There is a second approach. It's almost the same argument. But instead of saying they're relatively prime, what else could you say? Well, I mean, in some sense, if they're relatively prime, it's already reduced. But you're close with the most something. You could say with the smallest b. Right? Look at all fractions a over b. Method 2. B is minimal among all representations. And they're really extremely similar. And of course, if b is minimal, then a and b must be relatively prime, or you could reduce b further. And there must be some minimal representation, because as soon as there's 1, you now have an upper bound for b, and just try b equals 1, 2, 3, all the way up to whatever that upper bound is. But for some problems, it is a little bit nicer to talk about some kind of minimality property and going from that. The contradiction you get is essentially the same in the two cases, so I'll go with method 1, that they're relatively prime. Okay, so we'll do method 1 proof. So if the square root of 2 equals a over b, that implies b squared is 2a squared. What can we deduce? Why? So why do we know b is even? You're correct, but why do we know that? Okay, so why does that imply b is even? So the claim is correct, that b squared is even implies b is even. When the Greeks proved this, I think they only proved up to like the square root of 17 is irrational. How do you prove this? Proof. If b equals 2m, then b squared equals 4m squared is even. If b equals 2m plus 1, then b squared equals 4m squared plus 4m plus 1, which is odd. Therefore, b is even. It's annoying that you have to do this extra step. And this is what hurt the Greeks in general, is how do you prove in general if I replace this with a number that's not a perfect square? Let's just say maybe the square root of a prime. So I have your b squared equals pa squared. I want to show if a prime divides a product, then the prime divides at least one of those terms. So you really need a result along those lines. It's not a horrible result to prove, but it's a result you have to prove carefully. Often unique factorization comes in a lot of the proofs of this. Sometimes Euclidean algorithm, but you need something like this. So we can write b as 2m, therefore 4m squared equals 2a squared, therefore a squared equals 2m squared. Therefore, same analysis gives a even, contradiction as 2 divides a and 2 divides b. So this is the standard proof. Okay. Has everyone seen this proof before at some point in your life? Okay. So what I want to do now is I want to talk a little bit about different geometric proofs. And so I want to give a geometric proof, and I think I first saw this at a colloquium talk at Williams, where a student was giving 6 different proofs of the irrationality of 2. Square root of 2, sorry, square root of 2. So this is due to Stanley Tenenbaum, or at least he's the first one I know to have isolated this from the 1950s. And then you can ask yourself, how similar is the proof? So square root of 2 equals a over b. So let's assume this. So, so b squared is twice a squared. So let's look at what this means geometrically. I would start off with a square that's b by b. And this is telling me that the area is the same as 2 squares of length a by a. So the question is, where should we draw those 2 squares? Yes?
Could we try and make a Pythagorean triangle?
We could, though. The problem is, how are things going to fit together in terms of the angles? I mean, I love getting right angles, but if we try to put this in, it's going to come over. There seems to only be one natural place to put the first square. Where should we put, well, two natural places. One is wrong, one is right. Where do you think you could put the first square? What would be your possibilities? So I've got the square. Where might you put the first square inside this bigger square? Yes?
Like maybe tuck it into the top left corner.
Yeah, one possibility is the top left corner. Yeah, the other 3 corners are just absurd. Top left is absolutely the way it should be, and that's in fact how I have it in my picture. What's the other place you could put it? Not in a corner, but center. But that's just. But those are the real 2 places. The center is a nice point of symmetry. I can put one in the corner like this. So here's A, and I'll. Oops. And I'll put another one over here, A and A. And then this is, of course, an incredibly badly drawn picture. So I'll fix it up a little bit like this. Okay. That picture is now a little bit better. So the area of the big square is the sum of the areas of 2 little squares. So I will write not to scale. We've double counted this region. We haven't counted these regions at all. So the area of this region must equal the area of these 2 regions. Again, not to scale. So if you want, I'll try to draw it a little bit better. So A must be larger than I thought. So A must really be coming down maybe more like this. Now I'm probably overkilling, but so now those would be overkill, right? So where should I put the A? So that was too high. Maybe something like this now might be reasonable. So something like this. What's the dimension of this piece over here, that small square? That's b minus a. And so this would also be b minus a over here. What's the dimension of this over here? Okay, why 2a minus b? So we've got the two little ones like this. This is b minus a by b minus a, and we have two of them. And then we have a little bit bigger one. And we need to figure out what the dimensions are of this one.
2a minus b?
Okay, so how did you get 2a minus b?
So I did b minus 2, b minus a.
Good, because this thing over here is the same as down over here. So this whole horizontal is b, so this is b minus twice b minus a. And then that's going to become a minus b, 2a minus b, right? What should be true about these measurements b minus a and 2a minus b? They should be positive. Well, b is greater than a, so this is at least positive. Good. We think a over b is the square root of 2. So if I divide by b, I get 2 times a over b minus 1. 2 times the square root of 2 should definitely be greater than 1. So I'm not too worried about these being negative numbers. But that could come up to play later on. So now we know this plus this must equal this. What can we assume about the numbers a and b? They're minimal. So assume b is minimal. And so now we would get twice b minus a squared equals 2a minus b squared. So now the geometric proof has become algebraic. So if we expand things out, what do we get? We'll get 2b squared plus 2a squared minus 4ab equals, on the other side, 4a squared plus b squared, hopefully minus 4ab. All right, so the minus 4ab's cancel. We'll get a 2a squared on this side and a b squared on the other side. I'm getting a little worried right now. Oh, no, this is good. This is good. This is what I want. Right? So I'll get b squared equals 2a squared. So square root of 2. Wait a minute, did I mix up?
No.
Oh, I think I mixed up over here when I wrote a over b.
Yeah.
I mixed up a and b. Because b is the longer length.
Didn't you draw b as the longer one?
I drew b as the longer length, but over here I wrote square root of 2 is a over b. So no one noticed this, sadly. So this is why all the numbers are not matching. This is why I'm shaking my head internally. So we'll get square root of 2 is b over a. So everything is consistent. These really do match up. Well, they should, because we're assuming the square root of 2 is b over a. How is this a contradiction?
When you wrote, like, the first line at the top right part.
Right here?
Yes. So we can rewrite this as square root of 2 equals 2a minus b over b minus a, and probably we can show that 2. So are we now assuming a is min?
Right, so we should now be assuming a is min y. I wrote things backwards, which is quite annoying. So the contradiction is not in the algebra, it's that we've now found a potentially smaller way of writing square root of 2. So this just checks, yes, it's square root of 2, but now let's check and see, do we actually have things that are smaller? So the proof is fairly similar. So we now have square root of 2 is 2a minus b over b minus a. And this will be smaller if b minus a is strictly less than a. Or if b is less than 2a. But we're assuming the square root of 2 equals b over a. So b is equal to a root 2, which is clearly less than 2a. Contradiction. So this proves that if we can write our square root of 2 as a ratio of two integers where the denominator is as small as possible, we could actually find something with an even smaller denominator. And thus square root of 2 is irrational. Right. I do apologize, in the drawings I do, everything has a and b flipped, where a is the... Oh, wait a minute. Oh, actually, in my notes, I actually have the ratio is b over a. So, okay, that's probably why I was drawing it like that and I just wrote it the wrong way. Good. So this will at least match the paper. Any questions on this?
Can you go for that part again?
Sure. So the only way that this is a contradiction is if this square and all the new sides have smaller integer lengths. Because I've written square root of 2 as b divided by a, where a is the smallest integer, such that b over a equals the square root of 2. Well, this shows over here this relationship is correct. If we assume b squared equals 2a squared, this is also true. And now we can write the square root of 2 is 2a minus b over b minus a, which is what we have over here. So now we want b minus a to be smaller than a. If so, we've then written root 2 as a rational with smaller denominator than before. And that's the goal, is we got a smaller denominator than before. So this shows new denominator is smaller than old. And that's a contradiction. So this is a problem-solving class, and I've already clued you a little bit. One of the things you want to learn is when you see a result, you want to think, how can I generalize? How can I extend? What else can I ask? This was done in the 1950s. I have corresponded with the son of Stanley Tenenbaum, about his father's proof. And he is justifiably very proud of his father's proof. I hope someday my kids will be justifiably proud of some of their dad's proofs. But what's some natural questions you could ask about this method? Yeah. The Greeks had trouble with square roots of numbers. Could the Greeks have done this? And again, the Greeks had a very different way of writing proofs than we did. They were not doing things algebraically. But you do things all in terms of lengths. Can you show? What other numbers could we show? What do you think the next number to try would be? Square root of 3. And I think I might have commented that Professor Morgan was sitting next to me during the talk and had remarked that it was a shame it doesn't work for anything else. And a nanosecond after the talk, he might have received a napkin or a piece of paper with the following scribble on it. But not, of course, during the colloquium, because we would pay complete attention to the speaker. Any thoughts as to how you might attack square root of 3? We got square root of 2 by looking at squares and having this intersection. How might we try square root of 3? Okay, with what? What shape?
You say the square root of 3 equals b over a, right?
I just want to make sure I'm using the same notation as before. Okay, so I'm still keeping a as the longest side. So I want to assume that this is b over a. So what shape do I draw?
Well, seeing that I just saw your
Okay, if you just saw the paper, you're not allowed to speak. When I was in high school, my Spanish teacher one day was reading something, and on the back was the list of the pop quiz topic for the next day. And so I memorized my Spanish talk with mistakes and pauses, because if I gave a perfect presentation, and I know this is now being recorded, no, of course I would never do something like that. Okay. What shape should we use if you have not seen the back of the piece of paper? What shape should we use to get square root of 3? What shape do you think of when you see a number like square root of 3? Triangle. What kind of triangle? Equilateral. So let's take an equilateral triangle. So for the square root of 2, we took a square and we tried to put 2 squares inside a square. What do you think we want to do for an equilateral triangle? 3 triangles. Where do you think we should put them? Yeah, put them in the corners. There's really not that much mystery here, right? Boom, boom, boom. Okay, again, not to scale. And so we'll call this whole thing A, and we'll call this over here B. So this would be B over here. This triangle.
Shouldn't you make the fraction A over B then?
A is the longer side, right?
A is the longest side, yes. I wanted A over B. Thank you. I keep drawing it though. Okay, yes. So I want root 3 to be A over B. So A is the longest side. So this is double counted. This is double counted. This is double counted. This is counted not at all. So these 3 triangles must have the same area as that central triangle. So what would be the side length of this? So we need the dimensions of this triangle. So what would that be? 2b minus a, because if it's 2b, I would have this plus this. I've double. Wait a minute, 2b minus a? Yeah. So I would have this. I would double count this. If I subtract a, I'm left with just that. So this would be 2b minus a, 2b minus a. And then we have the one triangle in the middle. What would the dimensions of that be? Good, b, because this whole thing here is b. And I know that this over here is 2b minus a. This is 2b minus a. So it would be b minus twice 2b minus a. So this is going to become a negative 4. So it's going to become a minus 3b and a 2a. So I think it's going to be 2a minus 3b, 2a minus 3b. I'll just double check and make sure that the algebra has worked. I don't even bother writing it. I just assume it's going to work. Okay. What do we need to assume about these numbers? Positive. So is 2b minus a positive? Well, let's see. We have root 3a equals, root 3b equals a. So if I want to look at, I want 2b minus a, is this greater than 0? Well, this is the same as, is 2b greater than a? But we know square root of 3 is less than 2. As 2b is less than square root of 3b, which equals 2a, all is good. So we know that this triangle has positive sides. What about this one? We want 2a minus 3b. Is that greater than 0?
Now you do the same thing, except you're testing if A is greater than 3/2 B.
So now this is the same. Is a greater than 3/2 b? But we know a equals root 3b. And if you square 1.5, what is it, 2.25? So so we know a equals the square root of 3b, right? So a equals root 3b, which is greater than 3/2 b. It works. We can prove the square root of 3 is irrational, geometrically.
Why do we need to check them? Like, just to make sure we're not squaring negative numbers?
So it's a good question as to, I mean, doesn't this method just prove that every number now, the square root of all these numbers are rational? All right, let's try the next one. What number should we look at after our success at the square root of 2, square root of 3, square root of? Okay, we're going to have trouble proving the square root of 4 is irrational. All right, so maybe square root of 4 is bad. What should we try after square root of 4? Square root of 5.
Favorite shape.
And what shape should we use for square root of 5? A pentagon. And so I will just walk this over to, so the paper is online. Some of it doesn't seem to be displaying too nicely, but you can actually do it with pentagons and kites and whatnot. One of my small students, David Montague, was able to get this a couple of years ago. And the argument can show that the square root of 5 is irrational. What about square root of 6? What shape?
Can't you just say if root 2 and root 3 are irrational? Could you do something to prove root 6 is irrational?
So you may need to do something involving root 2 and root 3, but maybe, because root 2 and 5 over root 2 are both irrational, but their product is rational.
Root 2
And 5 over root 2 are both irrational, but their product is rational. So I like the idea of trying to combine. We've got root 2 and root 3 are irrational clearly together there. But unfortunately, we may not be able to do that. Any thoughts as to what shape we could do for 6? So hexagon is a natural thing. I haven't been able to make the hexagon work. I haven't tried too hard. I will make this a really nice extra credit problem. Can someone make the hexagon work? Now, unfortunately, if you get the hexagon to work, what number do you work on next? The septagon. Can you make this work? So I will make this a significant grade boost. If you can get, say, 3 different numbers that I have not been able to get before, that are fundamentally different. So I'll consider, for instance, 7, 11, and 13 fundamentally different. 7 and 14 I will not consider fundamentally different. I will boost your grade in the class by a third, so long as it doesn't push us above an A+. The way I was able to get 6 was to use triangles again. And so now I want to do this somewhat carefully, so I want to do 3 lines. And then I think I want to make it a little bit longer. So I'm going to start off like this. And then, actually, sorry. Yeah, I drew it a little bit off, sorry. That's right. So here's the line. I need to start off a little bit above the line and come down. A little bit above the line and come down. And then I think this point is also a little bit above the line and coming down, like this. And then over here, for this one over here, I'm going to come in like this. So now, if we look at things, this triangle, how often is this triangle counted? Twice. This triangle. This triangle. This triangle. This triangle. Twice, and this triangle. How often is this triangle counted? It's not counted. 0, 0, and 0. How often is this triangle counted? 3 times. All these small triangles are the same size. And these 3 triangles are all the same size. So what we would get is, we'll say, S is the small and L is the large. How many small triangles do we have? We have 6, but I would say it's actually not quite 6. I would say it's not quite 7. I wouldn't say it's 15. Because some of them we need, right? So for this triangle here, we need one of it to fill out the square, but we have one extra. So a better way to phrase it is, how many extra small triangles do we have? We have 8 extra smalls. And how many larges do we have? How many extra larges? 3 larges. And here's the trick. This is the same as 16 smalls equals 6 larges. 16 is a perfect square, so now I can get things about the square root of 6. So if you want, you can read the paper. It's not that hard of a paper to read on how to push these geometric arguments further. And we can now get the square root of 6 is irrational. I believe we can get the square root of 10 is irrational by looking at a bigger triangle. Anybody know these numbers? So we have 6, 10, and we had 3. Where have you seen these numbers? These are the triangle numbers. And in fact, you can see the triangles coming in. What's the next number we should look at? 15. So we could probably draw something like this again. What's the next triangle number? 21. Next triangle number. Next triangle number. So we just added 6. Now we have to add 7. So is it 35? We just added 7. Okay, so now we add 8. So it's 36. Next one. So can we prove all triangle numbers that the square root of them is irrational? Yeah, there's 36 right here. This is why I wanted to go at least this far. It turns out some triangle numbers are perfect squares. So there was a question earlier as to why are we spending so much time showing that these side lengths are positive numbers? The method I'm giving you must somehow break down some way when I get to 36. I should not be able to prove the square root of 36 is irrational. Okay? So I'm going to stop over here in terms of the geometric analysis. So if you can do 3 different numbers that are fundamentally different, I will bump your grade up a third. The other option is to prove something like the cube root of 2 is irrational. Can you do a 3-dimensional proof along these lines? I'd love to see something like that. Or a 4th root of 2. Maybe it's easier to work in 4 dimensions than 3. How far can you push this? How far can you push these geometric arguments? It's interesting, I think, to figure out why is it breaking down over here? It's got to break down somehow, because triangle numbers, they're the form, n plus 1 over 2. There can be squares. Will it work for every triangle number that's not a square? Does something special happen at 36? We don't have enough time to delve too deeply into that, but if you're interested, I'm happy to meet with you and chat with you about something like that. Okay, any questions on this? So I will just end with, have I given you the Morley's theorem speech? Okay, so this is from when I was in grad school. I will try to just put this up. So Morley's theorem is a beautiful theorem. It says if you take any triangle and trisect the 3 angles, you'll get 6 lines. For each side of the original triangle, look at the 2 lines, the 2 trisecting lines that are closest to that side, and that gives you a point of intersection. So you end up having 3 points of intersection, and that forms a triangle. It turns out that that triangle is always equilateral. And so we were chatting, myself and 2 of my friends, as we were walking into the graduate department at Princeton many years ago, and this came up and said, oh yeah, there's a really easy proof, because I'm a smartass. They go, oh, I don't know any easy proofs. What's the proof you know? I said, well, what you do is you write down the coordinates of the 3 points, calculate the coordinates of the points of intersection, calculate the squares of the lengths, and just show that they're equal. So my friend Eduardo bet me not that I couldn't, but that I wouldn't have the patience to finish the calculation before I graduated. If I'm able to do it, he owes me dinner not to exceed $12.50. If I cannot do it, I owe him an ice cream not to exceed $2.50. It took me about 1.5 years to finish doing the calculation. I found the best angles to use is like tangent of 1/3 of the angles. You keep clearing denominators every time you have lines intersecting. And I believe you end up with polynomials of degree like 48 and 2 variables. You expand them out. And then if you have 2 finite polynomials, the only way they can be always equal is if all the terms are the same. So you then subtract one from the other, and you show that everything cancels. I was allowed to use a program like Mathematica to expand things out. So I have basically 1 page of calculations of writing down the lines, and then I think about 40, 50 pages of Mathematica printout, just expanding everything out, and then at the very end, 0. So that is a proof of Morley's theorem. It is an absolutely horrible proof of Morley's theorem, and at the end of the day, I have no better understanding of why it's true. The first thing about problem solving is to solve the problem. Then, once you solve it, then you can have the luxury of talking about, is this a good solution? Is there a better solution? Is there a more illuminating solution? Does the solution generalize? What else could I do? John Conway has a phenomenal proof where he starts with an equilateral triangle and does a reverse construction to get your original triangle. It's a much, much nicer proof. But I thought this was just worth showing as a warning on arguments. All right. So we're going to switch now to the pigeonhole principle. So there's a lot that we can do with the pigeonhole principle. There's incredible applications. So do you want to do an application first, or do you want to do another pigeonhole problem? Problem, okay. In life, first loud voice often wins. All right, so the problem I wanted to do was, so pigeon problems. So S is a subset of 1, 2, and I'm going up to 2n. The size of S equals n plus 1. Prove there exists A and B in S such that A divides B. So one of the big things when you do pigeonhole problems is to realize, when is it a pigeonhole problem? Have I given you my speech on solving differential equations? Okay, so I taught differential equations. My first year at Williams, my daughter had just been born, or was born early in the semester, and I basically viewed teaching differential equations as dealing with a newborn baby. The baby is crying for some reason, and you want to figure out why. Does the baby want to be held? Does the baby need a new diaper? Does the baby want a bottle? Does the baby need to be burped? Does the baby want to watch the Red Sox? You go through all the different possibilities, and eventually, hopefully, one of them shuts up the baby. For differential equations, is it solvable? Is it exact? Is it, boom, boom, boom. You go through all your techniques, boom, 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 boom. You want to master a bunch of techniques. When you see a problem, does this look like something I should try to do by induction? Does this look like something I should try to do with a pigeonhole argument? Does this look like this is an inequality problem, and maybe I want to look at some kind of dimensional analysis and put in some, let's assume the product is 1 or the sum is 1, something like that. You want a bunch of things to just try and see if they help. When you see something like this, when you've got a set and you have something of a certain size, you should start to think, maybe this is a pigeonhole argument. What would happen if I made this number smaller? Usually these numbers are chosen for a reason. So there's always 2 questions to ask. One is, what are the boxes? And 2, second question, what are the pigeons? It's amazing sometimes just explicitly writing this down and trying to very explicitly state what these things are makes the problem a lot easier. So what do you think the pigeons are for this problem? Yeah.
Sorry, what's the definition of size again?
Oh, it just has n plus 1 elements.
So it's cardinality?
Right, has n plus 1 elements. So what do you think the pigeons would be for this problem?
Is 2 necessarily an element? Because I solved it already.
I'm sorry?
Is 2 necessarily
of S?
Yeah.
Doesn't have to be. S is a subset of 1 through 2n.
Oh, it's a subset.
We're choosing n plus 1 elements. Now, if I choose one specific number, the problem is very easy.
It's just one.
So if I choose, but this is now doing it by a case analysis. Case analysis is one of our proof techniques, but it's exhaustive, literally. You have to exhaust every single case. So one possibility is case 1, we choose the element 1. We're done. Case 2, assume 1 is not chosen. Now we have to choose n plus 1 elements from 2 through 2n. What if we choose element 2? So let's start doing the case analysis. Okay, so case analysis. Case 1, 1 is in S, trivial. Because if 1 is in S, then any other number is going to be divisible by that. Take 1 to be A. So case 2, 1 is not in S, and maybe 2 is in S. Now that 2 is in S, what must be true?
All the other ones have to be odd.
All others are odd. All other elements of S odd or trivial. How many odd numbers are left? Only n minus 1 odds left. As 1 is not an element of S. Right? Contradiction. So we must have another even. What's the next case? So case 3, 1 and 2 are not in S. 3 is in S. So now we can't have any multiples of 3. But then we can start cycling back. Right? Now we could maybe have 4. That's not so bad. We could also, okay, we can't add 6 because 6 is a multiple of 3. Could we add 12? No, it's a multiple of 3. We can't add multiples of 4 now, right? But this is beginning to get painful in terms of looking at all these cases. So we want a cleaner way of looking at these problems. So I think it's clear that the pigeons are the elements of S. So for us, for 2, the elements of S are the pigeons. We have to figure out the boxes.
You could say it's a pair of a number and twice that number.
Okay.
Because you can't have both a number and twice that number in S, which means that you have to take one from each pair, but there's only n pairs when you have to take 2 from one pair.
Okay, so one idea is to look at pairs. So we would have 1 and 2,
And then
2 and 4, 3 and 6, 4 and 8, all the way down to n and 2n. So we have n pairs, right? We can only choose one element from each pair. Now, if we choose 2, that actually gives us something in 2 different pairs.
Right, but in our best case, if we want to get the maximum amount of numbers out with only choosing one from each pair, you're going to get n numbers out.
Right. So this seems like this would work. That these should be the boxes. If choose n elements, best is if never have 2 in the same pair. No option for next. for the next point. So that would win. So this would be a good set of boxes. So how did you come up with these as the boxes? There's a problem?
Yeah, because not all elements are in the boxes. So we have n boxes. And
Ah.
so of course we have some numbers in that. So like 2 and minus.
So here's the problem, right? So which elements aren't in the boxes?
So all odd numbers.
But n plus 1, n plus 3, n plus 5, 2n minus 1 are not in any box.
I mean, I was thinking of doing some sort of multiply too, because it goes up to 2n.
Right.
And the size is 2n divided by 2 plus 1.
So this is close to what works. The reason it doesn't work is the boxes are not exhaustive. But a small tweak of this will work. And the idea is to go back to what does it mean for A to divide B? And so you were trying to get, one of them is twice the other. Another way of looking at this is A divides B. Say A and B have the same odd part. So if A and B, you can write them as a power of 2 times an odd number. So maybe A is 2 to the n, can't do n, bad choice, 2 to the I times an odd, and B is 2 to the j times an odd. If these odds are the same and I is less than j, then it will divide. How many odd numbers do we have? We have n. What we can do is our boxes will be the odd components. So given m in 1, 2, up to 2n, we can write m as 2 to the I times 2 to the L plus 1. And so the boxes will be the odd box. Box 1 is just powers of 2. Then box 2 is powers of 2 times 2 times 1 plus 1. Then box 3 is powers of 2 times 2 times 2 plus 1. No element is in 2 boxes, and all elements are hit. So no element in 2 boxes, all elements are hit. What you had before worked in terms of no element was in 2 boxes, but you didn't have all elements were sorted. So now we have n boxes. At least one box has 2 elements. So by Pigeonhole, at least one box has 2 elements chosen. And now that we have 2 elements chosen, they both have the same odd part, and one of them is going to have a smaller power of 2 than the other, so you're now going to have your division. So you'll have maybe 2 to the I, 2L plus 1, and 2 to the J, 2L plus 1. And that will finish the proof. So the hardest part about the pigeonhole principle is finding out where to choose your boxes, where to choose your pigeons. Usually the pigeons is a little bit clearer because you're given some set and you're given some number. But it's trying to figure out how do I want to divide things. So we will definitely do more problems along these lines. Okay.